In this video, we're going to talk about how to construct linear functions, or write down formulas for linear functions, given different types of information about those functions. One way in which it's possible to construct a linear function is by specifying its slope and so-called y-intercept. Another related way is by specifying the slope of the function and a point through which the graph of the function must pass. And yet another way of constructing a linear function is by specifying two different points through which the graph of the function must pass. As we'll see soon enough, these three different ways of constructing linear functions are all related to one another, but one thing to note for the time being is that they all depend on specifying precisely two pieces of information. Indeed, recall that any linear function can be put into the general form ax plus b. And so the fact that two pieces of information are needed to construct a linear function shouldn't be surprising, because algebraically there are exactly two free parameters to work with, namely the constants a and b. Let's consider the three different ways in which it's possible to determine a linear function, one at a time. What we're looking at here is the graph of a certain linear function, right? A function of the algebraic form ax plus b. As we know, the slope of that linear function corresponds precisely to the coefficient of x. It is exactly equal to the number a in the formula ax plus b. Moreover, any linear function must cross the y-axis. The point at which a linear function does cross the y-axis is known as the y-intercept of the function, and that happens to correspond exactly to the constant b. Indeed, notice that the value of the linear function at x equals 0 is nothing other than the constant b. So the first general form of a linear function that we'll be considering is the so-called slope-intercept form. And it is the form that we have already seen, the form f of x equals ax plus b. The point is that we can now interpret the coefficients a and b in a very clear way. A represents the slope, and b represents the y-intercept. And so if someone were to ask us to express a linear function that has a slope of a and a y-intercept of b, we would simply have to take those two values and substitute them into this general form. And note that if we care to represent f of x as a dependent variable y, then we would simply write this as y equals ax plus b, or as many textbooks do, y equals mx plus b. But of course, whether we choose to call the slope a or m is just a matter of taste. Let's think about a different way to represent a linear function. Suppose that someone specifies a point in two-dimensional space. Let's say it has coordinates x0 and y0, and asks us to find a line that passes through that point. Well, notice that it's possible to construct infinitely many different lines that pass through a given point, simply by varying the slope. On the other hand, trying to determine a line simply by specifying a slope is no good either, because there is an infinite family of parallel lines that have any given slope. But it turns out that if you specify a point and a slope that a given line must have, then there's no wiggle room. You determine a unique line, or a unique linear function. And this leads us naturally to the second important form that a linear function can take, and it's known as the point-slope form of a line. And it reads f of x equals y0 plus a times x minus x0. This is the formula of a linear function that passes through a specified point with coordinates x0 and y0, and that has a specified slope, a. And notice how it makes sense, because indeed, if we were to substitute x0 in for x, then this entire second additive term in the formula would simply vanish, leaving an answer of y0. So x0, y0 is indeed a point on the graph of this function. And moreover, the coefficient of the x term, if we were to expand the second additive term, is precisely a, and therefore the slope of the linear function. So if someone were to ask us to express a linear function that passes through a given point and that has a given slope, we would simply break out the point-slope form for a linear function and substitute in the appropriate values. And as with the slope-intercept form, we could also express this as an equation involving two variables. Or, as many textbooks do, we could express this as y minus y naught equals a times x minus x naught, which is also a simple rearrangement of the point-slope form that you'll often see. Finally, notice that it's possible to determine a linear function simply by specifying two distinct points in the xy plane, x0, y0, and x1, y1. The question for us is, how can we use information about these 2 points alone to reconstruct and express a corresponding linear function? Fortunately, this isn't hard to do because we can easily work out the slope of the linear function. It will simply be y1 minus y0 over x1 minus x0. And once we've got the slope and a point through which the function passes, we can make use of the point-slope form that we just discussed. So if we're given 2 points through which a linear function is supposed to pass, then we can express that linear function using the formula shown on the screen. And really, this is just the point-slope formula of a line where we have written down explicitly what the slope should be in terms of the coordinates of our 2 points, and where we've chosen, for no particular reason, the point x0 and y0 to be the one through which the line passes, although it must, of course, pass through x1, y1 as well. I urge you, however, not to simply memorize this form, because it's very easy to reconstruct this formula if you already know the point-slope form of a line. Just take the 2 points that are given to you, then use them to compute the slope of the line, and then finally substitute everything into the point-slope form for a line to recover this formula. It's also important for us to note that x0 and x1 cannot be equal to one another here, because if they are, we would be dividing by 0 when we compute the slope. Make sure you understand, by the way, exactly why x0 and x1 cannot be equal to one another from a geometric point of view.